So yes, today's talk, my talk title is about few-shot continual learning for assistive robots. Sorry. Okay. So autonomous systems are a part of our daily lives. In the real world, we have a lot of different scenarios where we have robot systems, perhaps assisting us with tasks like kitchens or drones, factory workers, autonomous cars, a lot of different scenarios, or social robots. They're becoming a part of the real world. They're becoming a part of our lives. And hopefully in the future, they will be probably more involved. One of the things for these autonomous systems that has to be there is like the ability to be able to personalize to the environment and to be able to personalize to the needs of the users. So for example, if there is this butler robot, it is supposed to know the kitchen of its particular user, and it is supposed to know, well, the food option or the breakfast option that the user actually wants. So that's one of the key challenges for any autonomous system in the real world, that they are supposed to be personalized to the particular situation if they're supposed to assist people in their daily lives. However, in our daily environments, our needs and our environments will change over time. And if these systems are to be deployed over the long term, the system will probably have to change with these small changes. So for example, let's just say it is that butler robot or a kitchen type robot that is making me a smoothie. And I like apple, carrot, banana smoothie, for example, this one. And later, after some days or a month, I might get bored with this and I want a strawberry banana smoothie. Now the robot will actually have to adapt to that. It'll have to learn, it'll have to adapt to this change. That's like a change in my need. Another could be just the change in the context or the environment. For example, if it's supposed to bring a cereal for breakfast, just simply going with the household assistant robot. And say I used to put my cereal on my refrigerator because let's just say I didn't have a pantry. But later I got a pantry, I got these nice boxes and I put my cereal in there. Now, this robot has to adapt to this. Now, this is like one of the key challenges then for this robot to be able to adapt to this when it's supposed to be deployed over this long term for the user. And these changes obviously will happen obviously continually over time. Yeah. Okay, so then the goal of this robot or the goal of this particular system is to do continual learning to adapt to the changing environments and needs. So for this particular case, for this particular goal of my research, there are different directions that I took from the perspective of machine learning, cognitive science, and human-robot interaction. So that's really what my research is about. It's actually at the intersection of these three main ideas or main directions: machine learning, cognitive science, and human-robot interaction. And there are a lot of different cool research that happen in that area and from my PhD and my postdoctoral research. So today I'm going to try to focus on a couple of different directions that I focused on, which is continual learning from limited data. So developing models that can be machine learning models for continual learning, and that can also adapt using a limited amount of data. And second, how can we integrate these models into practical systems, like such as robots, to perform real-world assistive tasks? Okay, so I'll start with the main idea of continual learning. So for continual learning, there is assuming there is a machine learning model. So this is in the realm of machine learning. Any M with parameters data, and it is being trained on the labeled data from different data in T increments. So T could be time, and you have data coming in in a different stream, and each data in each increment would be belonging to a particular task in that increment. So for a classification task, this D of T at a particular increment, this task would be just the training images for object classification. And the labels for that, this is like the label set. So for example, in this case for task 1, it's the butterfly, the label and the images for that task, where each of that and the model will be continually trained on these object tasks. One thing to notice in strict continual learning settings, usually you don't have the overlap between the object images for different classes. So for example, task 2 would probably not contain images of task or classes in task 1. So for example, butterfly would not appear in this, but that obviously won't be true in the real world, but I'll get back to that later. Okay.
Ali, your voice is dropping out a little bit. I think you can try turning off your video if it's a bandwidth problem.
Oh, sure. Yes, I can turn off the video. Just a sec. Okay. Hopefully that would be good. But if there is, just let me know. Okay. Great. So is this good?
Yeah, sounds better. Go ahead.
Perfect. All right, awesome. Great. So yeah, so I'll start with then the continual learning. And one of the easiest way for this to achieve continual learning, where you are trying to train this model, let's just say any classification model. One easy way would be just to do fine tuning, which is that you keep training your model on data coming in continuously without any need for caring or without any care for the old data that the model was being trained on. This, however, leads to this the problem called catastrophic forgetting, in which the model would drastically forget the previously learned knowledge and any previously learned concepts when learning any new task. So for example, let's just consider this object classification task, where you have just 2 classes. You train your classifier. It's just a simple classifier with a decision boundary that is linear between the 2 classes for class 1, class 2. Now, let's just say I get 2 more classes in a new increment. And now I try to train my model on this to try to classify these 2 classes. Obviously, my boundary would be an updated boundary here. However, because of this new boundary, you can see that it has forgotten the ability to classify these previous 2 classes. And this is really what fine tuning would do. If you just try to train your model on new data, it will just forget the previously learned classes. Okay, so there are various different techniques to deal with this problem. One easy way to do is just to replay all of the previous data when learning new information. So that's one easy way. However, it leads to different issues like memory shortage. For example, you cannot keep storing a lot of high-dimensional images in perhaps the robot's onboard memory, if it is a robot, in a person's home, or there could be data privacy issues. So for example, if a company trained the robot or an autonomous car on a large amount of data, and then the user wants to train it on, let's just say, its own personalized objects, it might not have access to that data that the factory actually had available. And finally, if you do replay all of the data from before, so for example, if you train your model on, let's just say, ImageNet, which has 2.5 million images, and now you want to add 1 more class to your model in real time in your own. If you want to replay everything, you'd have to replay pretty much all the data, 2.5 million images of ImageNet with, let's just say, 5 more images of your own object. So obviously that wouldn't be feasible in a real world environment. So essentially you would have a limited amount of labeled data in the real world, obviously, because mostly the main source of information, the main source of supervision for these models would be human users who might be unwilling to provide a large amount of data, large amount of training data to the model. And therefore, it will have to learn from the small amount of data per task, while also avoiding catastrophic forgetting. So that's really the few-shot continual learning problem, that learning from limited data while avoiding catastrophic forgetting over time. So to deal with this, one of the first things I worked on in my PhD was related to this. Okay, so how can we get this inspiration from cognitive science? So particularly, how does the human brain learn continually? So for this, I focused on one particular theory. Now, there are different theories of learning in the human brain, in the particular hippocampus and the neocortex, but I'll focus on this one model. It's called the APCON model. And the main idea of this model is that whenever any episode, so essentially any stimulus or any sensory information comes in for the brain or the hippocampus, it will try to find a difference of this new episode from the previously learned concepts. And so this is called the memory-based prediction error. And if this difference between the episode and the previously learned concept is really small, then the previous concept is just updated using this, new information, which is a memory integration. And if the new episode is quite different from the previously learned concept, then there will be pattern separation, which means you just create a new concept using the newly encountered episode. So inspired by this particular idea, I developed this model called centroid-based concept learning. And the main idea of this model is that whenever the model, so in this case, my machine learning model is a clustering approach, whenever it gets a data for a class in a particular increment, we can start a clustering process where we initialize a centroid for the class by the first image in the training set. So whatever training set I obtained, let's just say it has 5 images, I start by the first image as the centroid. For the next images, I just simply calculated the Euclidean distance of the image from or the image's feature vector from the centroids of the same class from the previous increments or previously learned centroids. This is essentially the memory-based prediction error if I were to put that in terms of the cognitive science terms. And if this distance is below a predefined distance threshold, that's a hyperparameter. The closest centroid is just simply updated using a weighted mean between the new episode, so the new feature vector, and the previously learned centroid. So this is essentially like the memory integration process. So for example, in this case, we have these two classes. Note that the filled dot would be a previous centroid and a empty dot is the updated centroid, and X, let's just say the new feature vector. So for example, in this case, X was introduced here in this particular case. So if this distance was closest to this particular cluster, the centroid was simply updated by using the weighted mean. So this essentially is how the model will learn the pattern, memory integration part. And again, in case if there is, if the distance between the new episode and the previous centroid is lower, or higher than the distance threshold, then you simply just create a new centroid or a new cluster for that particular class, which is then would be the pattern separation case. And this process just continues as long as there are more images or more data for that particular class. In this way, so for example, one interesting thing is that you don't have to worry about interference between two classes, because you create separate set of clusters for each class. So there will be multiple clusters for each, let's just say, object class. And there won't be any interference because you're simply using the data of that particular class to update the centroids of that single class. So to perform some experiments, I use the CIFAR 100 dataset. It has 100 different classes, which is like a benchmark data set for continual learning, divided into different ways of increments. So for example, in the first case, you learn 2 classes per increment. So you essentially keep on going learning 100 classes with 2 classes, 5 classes, 10 classes, and 20 classes per increment. And then comparing is the state of the art. One thing was seen that CBCL achieved a huge accuracy improvement over the previous works, almost about 10 to 11% increase in accuracy. However, this green dot, and I probably green cross, I don't know if you can see it, I should have probably made it bigger. This is actually the batch learning baseline, which means this is the approach when it uses all of the data from like the 100 classes at a single time. So this is simply a CNN which is trained on all the data. That is still about I would say 6-7%, still higher. So that's still because CBCL suffers from some forgetting, but it's not catastrophic forgetting, which is this fine-tuning approach to the pink line, or purple, I guess. That's the fine-tuning approach, and it drastically loses accuracy because it's forgetting all the previously learned classes. And that was pretty much seen in all the cases. And CBCL performance also remained pretty much similar, irrespective of the total number of classes seen in each increment. Okay. So
Ali, could you go back to the previous slide, please?
Yeah.
Okay. So in these cases, you said the upper bound comes from training your classifier on all the on data from all the 100 classes. What's happening for the other lines? Are they not getting all 100 classes or data from all 100 classes?
So all the models are being trained. So all of these different lines, they're for different state-of-the-art works. So for example, this black line is the model that was published in 2019 at CVPR. It's called BIC. Sure. Yeah, so it uses, but all of the models are using same kind of backbone architecture and being trained on the same exact set of classes. So also, so for example, BIC in this case, black would get 10 classes in the first increment, and then 10 in the next, and 10 in the next, and 10 in, so it will continue like that. Some of them would replay, some of them do replay a partial amount of data from the previous classes. So for example, the yellow line EIL, this approach replays a small amount of data from the previous classes, so not all of it. So this would still be training on, at the end, like learning 100 classes, but it won't be training on all of the data of all the classes at one time.
Understood. Yeah.
Yeah.
All right. So I guess the key difference is that they're getting the data in increments, and not like if at the line corresponding to number of classes equal to 70, it's not like you have data for all 70 classes together.
No.
Okay, got it.
Exactly.
And so in your particular case, for CBCL then, how are you setting this distance threshold? Does that change with every increment? Is there like some policy to do that changing?
Yeah, that's actually a great question. Yeah, so this was initially set using a cross-validation on the first increment, which is like the base increment. After that, it's not updated, the distance threshold. Yeah, because like afterwards, I mean, I think it would still be, perhaps there could be a cooler way to update it afterwards. But right now, in this case, it was simply chosen in the first base class case, using cross-validation, and then just continued after that. But it still produced actually pretty good results. I did try to test it afterwards, but there wasn't like a huge difference in the distance threshold even later on. However, to be honest, it could be because the data set still is like, the data is still coming from the same data set.
Right.
So it might not be, but it would be interesting to see if two different data sets are combined, and then to see like what the effect of the distance threshold would be. So yeah.
Cool. Yeah. Thank you.
Yeah. Any other questions, or should I continue? Perfect. Okay. So continuing from that, so the CBCL model was developed for this few-shot continual learning case where you get labeled data in each increment, although it is a small amount of data. However, as I mentioned like before, in real-world systems, there won't be this specific boundary between these two tasks. For example, you only learn orange in the first increment and you never learn it again, and you only learn apple in the second increment, you never learn it again. In the real world, obviously, you'd have data coming in a stream manner where you can see instances of any object class at any time. So I'm still sticking with the object classification case. And one other thing is that there might be a lot of unlabeled data available, but obviously the labeling supervision is limited. So the humans still are not able to provide a large amount of labels, but you still have a large amount of unlabeled data. So in this case, there are approaches for active learning where a model, a machine learning model, observes a large amount of unlabeled data and can use some internal metrics to select the most informative instances from this unlabeled pool, and then query the oracle, or in this case, the human user, to label that data for the model. So in this case, the model can learn the most informative samples, but perhaps using less amount of supervision. So this could possibly help us avoid this idea of this like strict cases where you have an assumption where you have like all the label data available at the same time. However, active learning techniques mostly still were designed for like the batch learning case, which means they were not designed for continual learning. So therefore, they would still suffer from this catastrophic forgetting problem. However, there is another issue with this approach. So for example, active learning case would be simply, this is like a simple scenario of an active learning case where you train a machine learning model on a training data set, which you divide on your own into unknown classes and known classes. Unknown classes are chosen from the training data set. And you can train your model to predict n minus k classes or whatever you train the model on, and some one neuron is set to be like for an unknown class. So if it's a neural network, so essentially, if like your model sees a class that is unknown, it should predict that it is an unknown class rather than just one of these previously learned classes. However, the interesting bit is that if you do train your model again in the second increment, let's just say on new classes, now your model was trained on something that it did not know before. So this notion of being what an unknown class is or what an unknown instance is also gets lost. So essentially, it forgets this instance of the idea of what an unknown sample is, or the most informative sample in this case, if it is the uncertainty sampling. So there are these couple of issues. So to deal with this, I considered then the few-shot continual active learning problem. So for this, I will still define it, continuing from the previous case of continual learning. So in each increment, a CL model, in this case M again, gets mostly unlabeled data. So you don't have the labels, sticking with the object classification case. And then it can choose a few most informative samples to be labeled using an acquisition function. So this acquisition function could be anything, and we can talk about that later, where you get like a label of small amount of samples. Once the samples are labeled, you train your model on this labeled data set, where the classes in each of these increments, so the object belonging to different classes could also appear in later increments. So there's not that fixed idea that each object has to belong, each object class has to belong to each increment. So for this, I propose this ML model using the idea of uniform Gaussian mixture model. So it's actually kind of perhaps a next version of CBCL, but with a couple of other components added to work with this particular problem. So for this, I'm dividing my model into a feature extractor. For this particular case, the feature extractor was fixed. It was a CNN feature extractor, which generates some feature vectors for unlabeled data pool. And it then uses some acquisition functions to get the labeled samples, the labeled feature vectors. And then I use a Gaussian mixture model to learn about these object classes, and then later train a classifier using some of the samples from before. But I'll talk about these components in more detail. Yes, so for the GMM-based continual learning, so GBCL, I represent each class using a uniform Gaussian mixture model. So instead of now a simple centroids, you're learning a Gaussian mixture model for each particular class. And the idea is still kind of similar how we updated CBCL, that for each new data point in a class, the Gaussian mixture model would be updated in two different ways. So either you would, sorry, I'm just going to get water, sorry. Yeah, so sorry about that. Okay. Yeah, so in this particular case, whenever a new sample for a data class for a class would appear, you'd find the probability of that particular data point to belong to the Gaussian mixture model of the class. And if that probability is below a probability threshold, above a probability threshold, then you pretty much update the Gaussian mixture model. So essentially update the mean and the covariance for the closest Gaussian mixture component. Otherwise, you just create a new distribution with the mean as a feature vector and zero covariance matrix, because obviously there is no other data point in that particular mixture component. So here's kind of an example of that. So if you have, like, let's just say a small amount of data in the beginning, you create a single mixture component, so a single Gaussian distribution. Perhaps you get a little more data that was close enough or for the same, or could be represented using the same mixture component. So it just updated that same mixture component. So single Gaussian distribution. And same, you get more data and you can update it like that. However, when your data is too far off or it's too different from your previous Gaussian distribution, and it cannot be represented anymore by a single Gaussian distribution, so you create a new distribution with a new mean and a new covariance, and then you keep updating that continually for the same class. So it's, again, similar to in some ways to the CBCL process, but now you have a Gaussian mixture model rather than a single like a centroid. So this is so by the way, I just need to mention that the Gaussian mixture model is being updated using the label data. So I'll get back to how to get the labels because they're kind of interdependent. So I didn't know which one to start with. So I started with GBCL. Now to classify, to train the classifier model to make prediction on the known classes. The idea is that you train the classifier on the new feature vectors that were labeled in this particular increment and use a process called pseudo rehearsal on the Gaussian mixture of the previous classes. So in this way, you can what you can do is, like, you can sample the distribution, Gaussian distribution of the previous classes to generate pseudo samples and then replay that pseudo data and then the training data in this particular increment to train the classifier model. And that's, you can avoid the catastrophic forgetting problem on the classification task itself. So here's actually an example of pseudo rehearsal on the MNIST data set. There are two classes that I chose, and these are two-dimensional embeddings that were generated using an autoencoder. And here is the original feature space for the two classes. It had 11,800 images. Here are actually the generated samples using pseudo rehearsal on using the Gaussian mixture model. So this is with using a different number of clusters, just to show, like, even if you keep reducing the number of clusters, or if you use a smaller number of mixture components, you can still regenerate and keep the feature space that was originally kept for the two classes. So that was kind of interesting, and which is why it actually avoids the forgetting problem pretty effectively, as I'll go to that later on in the next slides. The next part then is, like, okay, so you updated your model, trained it on the label data, but now how do we get these labels, or how do we get these most informative samples? So for this, I use a combination of two techniques one is entropy-based sampling, and the other point is viewpoint consistency, which is applied on the Gaussian distributions of the previous classes. So for entropy, it's actually just the entropy formula for any new sample, which is an unlabeled sample. The idea for entropy-based sampling is that it should have a low entropy if it is already represented by any of the previous GMMs. So the probability obviously would then be very high if the new sample is very close to any of these GMMs, and thus it shouldn't be, it is probably not the most informative sample for this case. The second idea is the viewpoint consistency, in that the idea is that if there are different viewpoints of the same object available to the model, or to the robot in this case, let's just say, the idea is that if it is actually learned by the model, then it should generate same label for the same object from different angles or different viewpoints. And if there is this inconsistency between two different viewpoints, then the model should consider it as a perhaps an informative sample. And then using a combination of these two techniques, using a hyperparameter delta. So I use like a combination of both of these to use as a final acquisition function A of x, which uses the Gaussian mixture model of the previous classes. So then therefore, like you can get the informative samples by using this acquisition function and keep updating the Gaussian mixture model, which then helps with the acquisition function continually. And as you can see, this acquisition function itself is constant, so it actually directly depends on the Gaussian mixture models. So it doesn't, at least theoretically, it shouldn't suffer from any forgetting on its own in terms of the idea of informative samples. Okay, so to test the model, I performed experiments on two different data sets. So first was this core 50 data set. It has 50 different objects belonging to 10 different classes of so 5 objects per class. And these are some of the instances and how these objects were captured. So that for each object there is a small video which is captured. So essentially you have 400 training videos for each for the 10 classes, and then you have 150 object videos in the test cases. And for this case, for the few-shot continual active learning case, at each increment, I sampled 5 objects randomly from this 400 training videos, and then to get the most informative samples, I allowed the model to get, say, one object to be labeled at each increment. So therefore, the model gets 5 unlabeled samples in each increment, and it can get the label for one of these 5 unlabeled samples. So essentially, the model would learn one object at a time, or one object video at a time, over 400 increments. So here are actually the results of this experiment with a lot of different models. Some of them are from the previous case as well, and there is actually CBCL as well. So red line is GBCL. The green line over here is actually the baseline, the batch learning baseline, which actually replays all of the data of the previous classes. And as you can see, it's like actually producing, GBCL is producing very close to the accuracy of this particular the model that is using batch learning approach. And as it continues to learn, eventually after learning, so this is only showing the 70 classes or 70 objects, but when it reaches about 400 increments, it starts to first of all saturate, and it reaches about 83% accuracy. GBCL and FLB is about 84%, which is the batch learning baseline. Also note that CBCL is quite low compared to this the new GBCL, which means it might be suffering from some forgetting, or it might not be learning the most informative samples quickly. Another way to check the efficiency of this approach was to also see how many increments does it take for the model to learn all 10 classes. So obviously, if the model is looking for most informative samples, so it should find the samples of a new class every time if it sees it. So therefore, it should learn 10 classes pretty quickly if it is trying to look for these informative samples. So GBCL was able to learn these 10 classes within 15 increments, which was quite significantly different from some approaches, but the batch learning baseline took about 19 increments to learn the 10 classes, which is interesting because the GBCL did have an advantage over even the batch learning approach, which again, it wasn't designed for active learning, so it could be the reason in this case. So next, I performed another experiment. This was with a pepper robot in a lab type environment with 240 training objects and 60 test objects. And they belong to 20 different classes. Similar kind of results were achieved for this case, where GBCL was able to achieve similar accuracy as the batch learning baseline. So GBCL is blue and orange is the few shot learning baseline. CBCL is this purple thing, which is still kind of similarly below that GBCL. One other thing was interesting is that if you note that after 80 classes, the model is able to learn all 80 increments, the model is able to learn all 20 classes and achieves about 76% accuracy. And then later on in the later increments, this accuracy starts to saturate and doesn't really improve much because, well, the model is not really learning too many more informative samples, which is kind of interesting if you have models that need to be adapted quickly. This could be a nice approach. Okay, so that's kind of the end of the machine learning directions that I wanted to talk about. The next main direction I want to talk about is like, okay, so we can design these machine learning model that can learn from these static data sets. How can we develop practical systems that can use these continual learning models and integrate them to perform real-world assistive tasks? So for real-world tasks, let's just start with a household robot that is making a cup of tea. Just to perform this task, it requires a lot of different data streams and different tasks. Initial starting point for, let's just say, for making a cup of tea would be starting with object reasoning, which means, okay, so to make tea, you need, first of all, a pot, which is, first of all, you need to know what a pot is. So there could be different kind of pots. So this is the object recognition part or object classification. Where can this pot be found? So for example, a teapot could be found in a cupboard. That's the spatial reasoning or the contextual reasoning part. And then there's like the task reasoning, which is making tea involves heating a teapot on a stove. So now you have to kind of reason on the task itself. And then you can work on the action reasoning, like the affordances on how to grasp the teapot, and then the agent reasoning if this is related to the needs of the person. So for example, a person likes their tea hot, or maybe some people like it cold. So like the main challenge here, one of the main challenges, like you have to kind of worry about all of these different streams of and all of these different tasks and which are working together in a single system. Now, the difficulty would be a lot more, the difficulty would be even more challenging when these streams are all dynamic and they're interdependent. So for example, teapots might be changing over time. There might be more objects being introduced into the system. Perhaps teapot is being moved all over the place. So the spatial reasoning component will have to do with that. And then the task reasoning could be, I'm using teapot for something else, not just for, say, making tea or other things. And then similar could be done for other streams. So for this particular case, and this is like my postdoctoral research actually, I mainly focused on 3 different kind of reasoning tasks, which is object reasoning, spatial reasoning, and task reasoning for the framework that I was trying to develop. And the framework I developed is, this big framework for like a household assistive robot that can use the, in this case, a fetch robot. It can integrate a lot of different components of these continual learning of objects, spatial contexts, and task representations, 3 different kind of things together using the sensory data of the robot and closing the loop all the way back to actually performing actions using the robot's arm and the base of the robot. So I'll actually start with the different components. I'll mainly talk about the perceptual system, which first has to encode the RGB and depth information from the cameras of the robot and how to encode it. And then further is like a memory system, which is a dual memory system, and I'll go into detail of that. And then finally is like, how can this be updated continually? And then how can this be used to reason on to perform tasks for a particular user that can interact with this system using a GUI. Okay, so I'm going to talk about the perceptual system first, which is again taking the RGB data and then outputting the object categories that it sees in a particular location with the bounding boxes and the 3D coordinates, and then encodes it into a feature space that could be then used by the continual learning model to actually learn about these from this data. So for the perception and encoding component, for the perceptual system, I used an object detection and localization model, first of all. So whenever the robot sees anything from its camera, first thing it would have to do is localize these objects and actually detect them. Once these objects are detected, the next case is then to pass them through a CNN feature extractor, similar to the previous machine learning models, and then generate some of the feature vectors for these objects, and then store them later on into the memory. The next part is like, okay, so this is great and easy. We've already done this for objects. Now, how do we represent these contexts and perhaps the semantic tasks in terms of object categories and their location? So for example, how do we represent a kitchen? So for that, for this particular case, I represented them using the object categories themselves. So what object categories are seen in a particular context. So in this case, kitchen, let's just say it sees a cereal box and an orange. So let's just say I represent a kitchen, a particular location of the kitchen using these two objects. So these two object categories with the particular location in the kitchen would be represented using a single feature vector. So these feature vector then would be in a different feature space than these object representation. But these would still be in some feature space over there. Similarly, task representations, for example, a breakfast could be like a cereal breakfast could be represented using a cereal box, a bowl, and a spoon, and I guess milk box. So then that would be like represented using a similar kind of feature space. So the next part then is, so let's just say you do have everything encoded from the sensory data of the robot. Next thing is to actually learn from this into for this, I'm using a dual memory system where there is a short-term memory and a long-term memory, kind of inspired by the hippocampus and the neocortex learning through dual memory. So for the short-term memory, in this particular model right now, it's actually just storing the raw feature space of the input. Now, for this case, I'm going to talk about still only the objects, but you can note that this will be happening for the other two streams. So for example, the task representations and the context representations, they could still be being represented and updated into a separate short-term memory component. So there are, let's just say, 3 different short-term memory components, and all of them are being represented using a feature space. So in this short-term memory, you're just storing a raw data, which is then being decayed very quickly. So it's we use a small, I use like a small decay component using an exponential decay, which actually just the rate decays pretty quickly with time. And then if the memory is being not repeated, it decays pretty quickly, and then it's removed so that you have more room for new data coming in. And then if you have repetition within the representations or within the objects or the data that you're seeing, the model then consolidates them into the long-term memory. This consolidation process is currently still a clustering. So this is where the continual learning comes in. So this is actually currently a clustering process that was used in CBCL. So pretty much you generate centroids 4 different object classes, 4 different different spatial contexts, and 4 different task representations. So this is happening still for all these 3 data streams at the same time. So let's just say an object class gets updated. So the model actually adds a new, learns a new object class. So it will update obviously the feature space for the objects, and then because the representations of tasks and contexts are dependent object categories, so they will also be updated with that. So all of this would be happening continually with this update in the dual memory system. The next thing is that semantic reasoning and the task planning case. So like, how can we actually perform these tasks? So for example, if a task is to perform get a glass of milk. So for this, glass of milk is being represented by a cup and a milk, which then can be reasoned on that they can be found in the kitchen using the representation of the context, which are then obviously found in the household. So this is kind of the semantic map of, or the semantic map of the knowledge of the household environment in this case for a particular task of glass of milk, which is then connected with the metric map of the household. So this in this case is a SLAM map of a well, in this case, the RoboHub, where I actually perform these experiments. So there are just some tables that I use to represent these contexts for now. So there's a dining table, kitchen, and office. So this semantic map would then have to be connected with the metric map of the system. So we're actually where to physically go to perform this task, and then reason on it together to actually perform any of these tasks. So to perform these, to test the system, I perform it in the RoboHub, as I said. I use 18 different objects. So this is actually an example of the kitchen context for now. Obviously, it might be a little bit more complex in the real kitchen, but there are some challenges in this place as well because you don't have these kind of distractions in the kitchen environment. So, and there were 3 different contexts that I used: kitchen, home office, and a dining area. And the task representations were simply just some breakfast or like eating tasks, like glass of milk or a smoothie or cereal breakfast and stuff like that. And for this, I used different kind of experiments to test the ability of the system. I'll actually go into like just showing a couple of videos on like how the system actually works. So this is, let me just see if I can get this video going. Sorry, just 1 minute. I can't see the, oh, there it is. Okay. Sorry. Okay, so this is actually the example of how to teach. So this is the GUI I currently use, which this is like the example of teaching an object to the robot. So you can type it down here. If it is a graspable object, so you can also put that here. So in this case, I'm the one who's putting the book in front of the robot. Save this particular image for the book. And then perhaps change the direction if I want to provide multiple images for this book. So save it again and keep doing that for the book. However many times. I think I did like about 4 or 5 times per object in this case. And once it's done, I'm just going to try to skip it most of the video. I guess I'm showing it a lot. So the next is mouse hub. So it's the same process for the mouse, just showing different directions of mouse. Once it's done, it would end. Once that end button is pressed, it transfer these object data into actually the long-term memory when the human directly teaches it. Because sorry, I'm just going to pause this. So whenever the human or a user directly teaches this object, they actually get consolidated directly into the long-term memory, because the assumption is that the user is actually teaching the correct knowledge. But through unsupervised learning, that data goes directly into the short-term memory. The next part is just to kind of how to learn a spatial context. This is kind of a video of that. So the robot is manually driven to that spatial context first using a joystick. So assuming the user can do that, So in this kitchen, you have labeling that location as one. Location one has, let's just say in this case, cereal. Note that this is just the output of the YOLO detector that I was using. This is a generic detector, obviously, but I'm not really using the labels of these objects. They are actually being learned using the CNN feature extractor and the representation in the short-term and the long-term memory. And then similarly, I actually move this to this second part of the kitchen context, and then just moving it around just to make sure that the robot actually sees this object milk, which was a task. Sometimes it would just not detect these objects, which was actually the main source of error in the system. And then same would be done for the other location, like moving this to this final location. And finally, it's just to represent a task. It would be similarly, you just place it in front of the table, learn a task using the button on for the task, and the GUI in this pretty much learn that. Next, I'm just going to show an example of the system working to bring an object, but if this video loads, okay, yeah. So this is actually an example of the object search for an apple. This is after fully supervised learning. So the user taught everything, in this case me. I taught everything to the robot directly through the graphical user interface. There's no unsupervised learning happening, at least in this case. So I'm giving it the direction on the GUI to actually bring me apple. It's going to go to this location, apple autonomously. And then once it reaches it, it actually uses then again the object classification and the localization system to find the object in the local area. And then it goes and picks it up. I'm just going to quickly move it. And then just go back and brings it to this dining table type area. And this is like the office where you can see some marker or mouse. And I just pretty much places the apple back there. After that, it will move back to the neutral location where it was supposed to be before. The next is the, now the same case now, note that now the apple has been moved to a different location. So the robot actually goes, it's asked to bring an apple. It goes to the same location where it is supposed to see from the long-term memory. It goes to find apple there. It's not going to find it. So the next thing the robot then is going to do is start searching randomly, first of all, within the kitchen, where this apple might be. So I've kind of made it a little bit faster. So the video is a bit faster. It's going to go here in this area. Doesn't see his apple. Okay, goes back, goes to this particular area. So it's going to find apple. It's going to pick it up. And then it's going to take it back to the dining area. So the next thing I wanted to show is like how it can use this recent memories from the short-term memory now. Instead of now, so again, apple is being searched. I asked the robot to bring apple, but now, since it already knows that from recent memories in the short-term memory, that apple is found in this particular area, so it's going to go back here and find apple, and then goes and brings it back to the user. So I'm just going to quickly move it. But note that if it keeps seeing this apple in this particular area again and again, the short-term memory would then get consolidated in the long-term memory. So the location for the object would get updated into this particular area, although with some probability. But if it isn't repeated, and let's just say it was a temporary move, so then the robot would go back to the original location of the apple using the long-term memory. So one final thing I wanted to show before I end my talk is this adaptation of the same model. In this case, it's actually the same semantic reasoning architecture, but for a task of creating breakfast options. So instead of now just learning the breakfast options from the user and setting them up, the robot can actually use this the task representation for breakfast in the long-term memory and try to generate creative new options for the user. So the first part is actually just teaching the breakfast option to the user, which is very similar to the case I showed you before. So I'm just going to skip that and go to the setting up. So for that, this is actually the part where the robot actually sets up a known breakfast option, which is a glass of milk. And this is actually in a different location, in a different lab where we moved the robot upstairs in E5. So this is kind of a new setup with a new SLAM map, but the same objects. So the robot goes and set this up, this glass of milk. This is kind of just showing the robot using the short-term memory to actually set up some cereal breakfast. But I'll skip that and go to actually the more interesting bit, which is setting up or creating a new breakfast option for the user when the user just says, surprise me and give me a new breakfast option. So in this case, the robot now generates this option, which was never seen by it before. So it had seen milk and cup, but it never saw this particular setup. So it's now bringing this breakfast option with milk and cup and honey and banana. Note that this is being generated again used by sampling a Gaussian distribution representation instead of like the centroid. But with that, it still has to update the representations if they have some issues. For example, if it generates milk with honey and banana, it has to infer that cup is still needed to perform this, to create this breakfast option, because milk has to be poured into a container based on what the robot learned in from its previous interaction with the user. Yeah, and that's pretty much it. I am doing some more interesting research with actual human participants, but that data is still being analyzed. So I wanted to just end it here with my presentation. Thanks a lot. And if you have any questions, please let me know.
Thank you, Ali. That was great. Do we have any questions?
So I can turn my video.
Okay. I guess while others are thinking about their questions. So what part of the model, Ali, so in the last video that you showed us, what part of the model is it that tells the robot that you should have milk? If you pick milk, you should also pick a container.
Yeah. So this is actually something I added on top of that, the same model. So it's actually an adapted version of that. But I felt like I didn't have too much time to talk about it. But yeah. But the main idea for that is, let's go back to this part. So after the robot is asked to generate this new breakfast option, so another actually thing is added in this semantic reasoning part, which uses the conditional dependencies actually of the previous objects on each other's, so the task representation. So for example, if it's a representation of an app, milk and glass, or I'm just gonna actually turn off the video because I feel like my internet is unstable. Yeah, so if it has seen like a representation of milk with glass and milk in a cereal scenario, so it actually learns this dependency through these representation. You know, that milk is always supposed to be with a container rather than alone, and same with the cereal box. But yeah, I mean, I wish I could go more into detail about that model. Yeah. Yeah. But right now it's actually using a conditional probability to learn these dependencies.
Got it.
Yeah. On the previous representation of the tasks. Yeah. Yeah.
And I guess on the same note, so in the part where you ask it to surprise you, I guess it's sampling from the centroids that it has
yeah. So yeah, for this particular case of sampling, the task representation in that case are more a Gaussian mixture model rather than a centroid. Yeah, so because then you can sample it and then it might generate some random things for you. So some of those might be valid breakfast options. So for example, it has all these things like valid means like it has all these dependency issues fixed, but sometimes it might not, because it could generate some random setup which might not be a valid breakfast setup. So then on top of that, then you have to add this part here in the semantic reasoning phase to fix it. using the conditional dependencies of these objects within the task representation. So it's actually uses a combination of these two memory systems.
I see. And this semantic reasoning model, is it like, is everything in there learned from data, or do you also like handcraft some features or some rules to make sure that weird combinations are not selected?
That's all from data. So everything the user taught, it actually is just based on that. Nothing is being done manually or any logic-based reasoning, at least in this model. It would be interesting to use perhaps like a knowledge graph, like a concept net, to combine it with this local knowledge, perhaps. But that would be like a huge next step, because just getting the system to work with continually learning these streams was pretty interesting. Especially when the robot learns like a weird representation, it goes to a wrong location in the kitchen, or it doesn't detect the objects correctly. So it learns some weird combination then, which is cool, which is interesting.
This reminds me of some work that my previous colleagues were doing, and they're trying to essentially learn I guess logical representations of what it means to satisfy a task from human demonstrations. And they were using Overcooked. I don't know if you're familiar with that game.
Yes, I played it a lot.
So they were using Overcooked as the demonstration platform. And essentially they mined out there's logical specifications for what it means to, I don't know, make a good dish or whatever, or make a dish and deliver, something like that. And then they can use that for synthesis next up, like for example, they can use that for either synthesis or monitoring if their robot is doing the right thing or not, or if their AI is doing the right thing or not. So I wonder if you could bring something like that in here as well too, and as an additional layer on top of semantic reasoning.
Yeah, that would be really cool, because right now it's currently all database, so like directly from whatever the robot sees. But it doesn't have like the feedback from the user directly, like if it is actually like a satisfactory performance of the task. That would be actually really interesting to combine it with this logic-based reasoning, and then do the synthesis. I'll have to add some feedback loop from the user,
of course.
I guess over here, going back to this area. No, thanks, that's actually a great idea.
Do we have any other questions? All right, if not, let's thank Ali again. Thank you, Ali, and thank you all for attending and for your patience.